In this video, we're going to discuss the ideal gas law. So first, let's review our definition of what an ideal gas is. An ideal gas is a gas where we assume there are no intermolecular forces between the gas molecules. We also assume that the volume occupied by the gas molecules themselves is zero. So therefore, the volume of the gas will be equal to the volume of the container it's in, and there's no additional volume due to the gas molecules themselves. We also assume, when we're talking about an ideal gas, that the collisions between the gas particles themselves with each other or with the container are perfectly elastic. So there's no loss of kinetic energy when we have these collisions. Now, we make these assumptions when we're studying gases because it simplifies our calculations, as we'll see a little bit later. However, in reality, there are some intermolecular forces between gas particles, and their volume is not zero. So we have what we call real gases, and these are the gases where we cannot make these assumptions that there are no intermolecular forces and that the gas molecules do not occupy any space. So generally, for our purposes, when we're studying gases, we're going to be talking about ideal gases. But it is important to know that not all of these assumptions are valid under all conditions, and therefore we call these real gases. So when we've studied gases thus far, we've looked at three laws: Boyle's law, Charles's law, and Avogadro's law. Boyle's law showed us that the volume is proportional to 1 over the pressure. Charles's law showed us the volume is proportional to the temp in Kelvin, and Avogadro's law showed us that the volume is proportional to the number of moles. Now we can combine all three of these into one expression. If we combine all three of these laws into one expression, we get something that looks like this. We get the volume is proportional to 1 over the pressure, so pressure's on the bottom. Volume is proportional to the temp, so temp's on top. And volume is proportional to the number of moles, so the number of moles are on top. So we end up with this proportionality expression. However, this expression does not allow us to say that the volume is equal to these. So the volume is not equal to the temp times the number of moles divided by the pressure. It's proportional to them. In order to solve problems, we need some mathematical relationship between volume, pressure, temp, and the number of moles. So is there such an expression? Well, there is, but we have to add a proportionality constant, R, to this expression that we have here or here. So if we add in this proportionality constant R, it allows us to say that the volume is equal to the temp in Kelvin times the number of moles times this, what we call the universal gas constant, R, divided by the pressure. So this expression that we have here, where the volume is equal to temp, number of moles, R divided by pressure, is what we call the ideal gas law. It can also be written, as you see here, just rearranging to get pressure and volume on the same side. We generally see it more commonly as PV equals nRT. So this R, this universal gas constant, what is its numerical value and what units does it have and how is it derived? Well, in order to derive the universal gas constant R, there's a certain relationship that is very important. And this relationship tells us that if you take 1 mole of any gas, so 1 mole of any gas, and you put that gas at 0 degrees Celsius, which is 273.15 Kelvin, and at a pressure of 1 atmosphere. So we can take 1 mole of any gas at 0 Celsius and 1 atmosphere of pressure. That gas will occupy 22.414 liters. So this is a very important relationship. This volume, 22.414 liters, is what we call the molar volume of a gas. It's the molar volume because that's the volume that 1 mole of gas will equal at this temperature and this pressure. The temperature and pressure, the temperature of 273.15 Kelvin and exactly 1 atmosphere pressure is what we call standard temperature and pressure. So just to review, if you take 1 mole of any gas at standard temperature and pressure, it will occupy 22.414 liters. And it doesn't matter what gas it is. It can be carbon dioxide, nitrogen, hydrogen, helium, any gas under those conditions will occupy that molar volume. And we abbreviate standard temperature and pressure. You'll often see it just as STP. So here's a little chart that shows you kind of what we were talking about there. These are the molar volumes of some real gases at STP. So again, an ideal gas, it would have 22.414 liters at its molar volume at STP. You can see that all of these gases, their molar volumes are very close to that. However, there is some slight deviation because again, these are real gases, not ideal gases. But on average, an ideal gas, we can make its assume its volume to be 22.414 liters, again, at STP with 1 mole. So let's take a look at how we derived R. Now that we understand what the molar volume is, if we take our ideal gas equation, PV equals nRT, our ideal gas law, let's solve for R. If we rearrange the expression for R, we get our ideal gas law in a form that looks like this. We can plug in this relationship, this molar volume relationship that we just looked at. We can plug in a volume, a number of moles, exactly 1 mole. We know the volume that it will occupy. We know the temperature, 273.15, and we know the pressure. So we plug in a pressure of 1 atmosphere, our molar volume, 1 mole at STP, 273.15 Kelvin, and we solve for R. We get a value of, as you can see here, 0.082058. The units would be liters, atmospheres times liters divided by moles per Kelvin. So this R, as we mentioned, is the universal gas constant, and it's the same for any gas. And so this is the proportionality constant. This is the units. And using this proportionality constant gives us, allows us to say that PV is equal to nRT. So now if we have any of these, three of these variables, if we know the volume, number of moles, and temperature, we can mathematically solve for the pressure if we need to. So let's take a look at a problem involving the ideal gas law. Pause the video and see if you can solve this. Okay, so let's take a look at it. So we're given that we have a volume of 1 times 10 to the 5th liters at STP. So we know we don't have 1 mole. We're asked how many moles do we have. So let's write down what we know. We know our pressure at STP is exactly 1 atmosphere. We know the temperature at STP. That's a exact number, 273.15. That's a definition. Our volume is given. R is given. I've rounded it up just a little bit. So we always know R. That's a constant for any gas. And we're asked to solve for the number of moles, X. So we can take our ideal gas equation, PV equals nRT, and solve for the number of moles. Now all we have to do is plug in our values. If we plug in our pressure, volume, R, and the temp, we get a number of moles equal to, as you can see here, 4,461.36, or if we round it to the correct sig figs, we get 4,461 moles. Now the second part of this asks how many grams is that? Well, we can convert moles into grams using the molar mass. We know that this is methane, CH4, so I take my moles, use the molar mass to convert it into grams, and we get 7.157 times 10 to the 4th grams. So the ideal gas law is very helpful because it allows us to solve for, in this case, the number of moles if we know the pressure, temp, and the volume. And to use this, we have to know our universal gas constant. So be sure you practice some more of these problems and get familiar with the ideal gas law.